Okay, so thank you everyone for joining us today for the SFPE Hong Kong Student Chapter webinar. So today we have a great pleasure to invite a speaker, Dr. Shuna Ni from Utah State University. And actually, I have never worked with her, but her reputation stands out. So I know her name. So Professor Ni is, I think she did her undergrad in China and a master in China in Tongji University and a PhD from Texas A&M University. After that, he did her postdoc at Johns Hopkins University, and from last year, I think, she joined the Utah State University. And she is a civil engineer, but she did a lot of research related to the structure behavior in fire. So today's topic, she probably will introduce something very interesting about how can we evaluate the structure safety in fire environment. So I'll just leave my microphone to you. Thank you.
Thank you very much for the invitation for Dr. Huang and the topic of my today's talk. Let me share my screen first. So the topic of today's seminar is mainly talking about a risk-informed framework for evaluating the structural fire safety of buildings.
The sound is good. Okay.
Yeah, I try to minimize something. Yeah, it worked now. So here's a short introduction of myself, and I get my master degree and bachelor degree in China, and I get a master degree in Tongji University, and in 2012, and then I come to the United States for my PhD degree, and my research is mainly focused on the probabilistic structural fire engineering, and also I did some research about fire-related multiple hazards, and mainly focused on post-earthquake fire and post-fire earthquakes. And also currently my group's research also focuses on the fire safety of tall mass timber buildings. And we are also very interested in the research about fire forensics and the impacts of fire on civil infrastructure systems. So here, and for the structure fire protection, and it's one of the components of the fire protection of the building. For the fire protection building, it's including different components for example, the fire detection and alarm system, and the fire suppression system and the smoke control system. And the structural fire protection, it's one component of the fire protection building, and it's mainly to mitigate the risk of structural failure under the fire exposures. So there are two specific objectives for the structural fire protection. The first one is to provide the structural integrity under fire to ensure the life safety of occupants and first responders. And the second specific objective is to limit the structural fire damage, to mitigate the social economic losses. For example, if a vehicle fire happens under a bridge, and we would like to make sure the structure of the bridge will not be damaged too severely. In this way, we can reduce the transportation disruption time and thus can reduce the social economic losses. So the first specific objective is mainly related to the life safety, while the second one is mainly related to the function recoveries. So no matter life safety or function recovery, it all requires a framework which can comprehensively assessing the fire risk to a structure. Here, by comprehensive, we mean that such a framework, it can output the risk information or building at both the system level and the component level. And also we hope such a type of framework can incorporate the uncertainties related to the occurrence and the growth of fire, as well as the structural response. So such a type of framework, basically, it will provide a methodology for the risk-informed performance-based design for the structural fire protection of building. And the output of such type of framework, it also will facilitate the analysis of structure's recovery after the fires. So for the other type of hazards, for example, earthquake, they already have such type of framework. For example, this is a framework which developed by the Pacific Earthquake Engineering Research Center. And this framework, basically, their analysis following 4 steps: hazard analysis, structure analysis, damage analysis, and loss analysis. There are some existing research which try to adopt this framework for fire hazards, but there are some remaining challenges which needed to be addressed. So the first challenging is is because this framework, those existing framework, they didn't consider the spatial uncertainties of fire hazards. So when the fire happens, we don't know where the fire will begin, and also we don't know how the fire, whether the fire will be confined in a compartment or it will be spread to the other areas. And also those existing frameworks, they basically using binary failure criteria. Basically, they classify the building whether it's a failure or it does not failure, collapse or not collapse, which is not true, especially for some reinforced concrete structure. Reinforced concrete structure usually they have relative good fire resistance. Under the fire, usually those buildings will not collapse. But those non-collapse scenarios, they still require a lot of repair efforts. So we need to propose a more meticulous classification of damage states to corresponding to the gradual level of repair efforts for those non-collapse scenarios. And also those existing frameworks, they mainly analyzing the structure. They based mainly to analyzing the structure based on the individual structure component. For example, they analyzing one column, one beam, or a floor system. But in reality, each component within a building, they interact with each other. This such type of interaction will lead into some additional deformation and additional damage. So our framework also needed to capture such interaction between each component within a building. The next one is multiple physics. The fire damage is multi-physics in nature. So basically, it will have some damage for, take the reinforced concrete structure, for example. There will be some damage due to the thermal expansion, the expansion of a slab, leading to some lateral displacement of a column. And also there will be some section damage due to the heat penetrations. For example, concrete spoiling and cracks. And we needed to adjust both types of damages in our framework. So this is a framework we have proposed. It's also based on the PBEE methodology. But we consider the spatial uncertainty through a loop. Basically, we consider the different fire location, different fire scenarios. For each fire location, and our analysis also following 4 steps: fire hazard analysis, fire-thermo-mechanical analysis, damage analysis, and loss analysis. So in the fire hazard analysis, we may need to identify the probability that a fire happens in one location. And also we need to identify the intensity measure. Here, the intensity measure used in our framework is a fire load. While in the fire-thermo-mechanical analysis, we need to output the structural response in a fire in a probabilistic manners. And also, as we have mentioned, we need to analyze, incorporate the interaction between each structure component within a building. So that's why here we also need our framework analyzing a whole structure system rather than an individual structure component. So in the damage analysis, mainly it's based on the results. It's based on the results from the fire-thermo-mechanical analysis, and it will analyzing the probability of building collapse. If the building does not collapse, so we need to calculate the probability of a structure component at one specific damage state. Basically, we need to calculate such a quantity for each structure component and for each damage state. And the next step is the loss analysis. So now we have the different type of probabilities, and then we calculate the fire loss of this building. And the total fire loss for the building will be the weighted summation of the loss for each fire scenarios. So basically, in this first step, the fire hazard analysis, which it try to identify the probability of the fire happens in one location. And we mainly refer the methods recommended by the Euro code. So our contribution is mainly focused on the next three steps: fire-thermo-mechanical analysis, damage analysis, and loss analysis. Now I would like to give you more insight about the fire-thermo-mechanical analysis. So in this part, in this step, we try to output the structural response of building during a fire in our probabilistic manner for each fire location and each level of fire load. So in our deterministic fire-thermo-mechanical analysis, basically the analysis has three steps: fire analysis, thermal analysis, and mechanical analysis. So in the fire analysis, we analyze how the fire developed in our building, and those information we input into the thermal model as the thermal boundary condition to analyze the temperature distribution in a structure component or in a building. And those temperature data will input to the mechanical model as the thermal load to analyze the response or structure in the fires. So this is the deterministic manner, but in reality, uncertainty exists everywhere. So the opening or compartment have uncertainties. Mechanical load have uncertainties. Material property also have uncertainty. There are a lot of other variables have uncertainty. So in this step, we need to incorporate all those different type of uncertainties into the fire-thermo-mechanical analysis through Monte Carlo analysis or the other methods. So ultimately, we would like to output the probabilistic distribution of the building response rather than individual values. So as I have mentioned in this part, our analysis is based on the building systems. Here I would like to show you why we need to consider, why we need to analyze the whole building system. This is a 5-story building, and we analyze the structural response. We developed the building model for the whole building, and we analyze the displacement of each structural component in the under the fire. And if you look at this column, this one, and due to the thermal expansion of this slab, and this column have a very large lateral displacement. So the maximum value is up to 116 millimeters. Even when the temperature cool down to the ambient temperature, and the remaining lateral displacement is still have 79 millimeters. So this type of deformation cannot be captured if you're using isolated structure component analysis. If you just analyze this column, this type of deformation is very difficult to be captured. However, there's a problem. Since our analysis is probabilistic manner, right? So if we analyzing the building, the whole system, and running the scenario for 1,000 times, that will be very time consuming and it will require a lot of computation time. So what we have done, and we try to simplify the model, and our research have shown if your fire is just at the first story, and you don't need to model the other floor system. You just need to model the floor system above the region where the fire begins. And this is a simplified building model, and here's some comparison between results between the two models. And this is the result of the lateral displacement. At the top of the first story column, basically we have analyzing the lateral displacement at this location. At the top of the first story column. And the left side is the maximum displacement, and the right side is the residual displacement. And we compare the results from the two models, and they are very close to each other, no matter in the magnitude or the directions. And such a simplification has reduced the computation time by half, but it's not enough. So our next step is to develop some surrogate data-driven surrogate model to replace those physical models. But this is one of our future research directions. So basically, we would like to develop some data-driven surrogate model to analyzing the structural response of a whole building system under the fires. And also, as we have mentioned, we would like to consider the uncertainties, right? So the uncertainty, how to consider? We need to have a lot of probabilistic model for different variables. And the previous research have developed the probabilistic model for opening and for mechanical loads. Our contribution is to develop the development of the probabilistic temperature-dependent concrete model. So we cracked this concrete strength data from different literature and different previous studies. And here's those concrete strengths. Here the model we developed is the retention factor. Here the retention factor is the ratio of the concrete strength at the high temperature, at one specific temperature, over the concrete strength at the ambient temperature. So basically, we developed the probabilistic model for each temperature, the concrete data at each temperature. And ultimately, the parameter for the Wimble distribution will fit it as a function of the temperature. This is how we develop these probabilistic models. And the model probabilistic distribution we have used is the Wimble distribution. Actually, we have tried to compare the results from different distributions and figure out the Wimble distribution works the best. So this is a comparison of our probabilistic model with some deterministic model. So the black solid line is the media value of our model, and it's very close to the deterministic model in the yellow pose. And also we found that most test data follow with the 5% quantile of our model and the 19% quantile of our model. And this is a concrete temperature-dependent concrete model. And we also have developed the model for the steel and for the yielding strength, temperature-dependent yielding strength of the steel. And those probabilistic model have been incorporated to the commercial nonlinear finite element software. And this software is mainly specific used for the structural engineering. And so now I have talking about the fire-thermo-mechanical analysis. Basically, this step can output the response of the structure in a probabilistic manner. So based on these results, we can do the damage analysis. So here I would like to show you what damage we consider in this framework. So we consider whether the building, first we need to identify whether the building will collapse or not collapse. If the building do not collapse, we need to consider the damage in fire rate and the non-fire rate, and we need to consider the damage to structural component and the non-structural component and content. So basically, the output of this frame, of this step is first one thing is the probability of building collapse under the fire load QF and the condition on the occurrence of the fire in location I. And if the building does not collapse, and this step will tell you the probability of component at a specific damage state under the fire load QF and the condition to the occurrence of fire in the location I. So it's very easy to calculate the probability of building collapse, but the calculation of the probability of a component at a specific damage state require a lot of definition and require a lot of further development of this framework. So first, I the next slide here, I would like to show you how we calculate the probability or structure component at one damage state. So first thing, we need to define the damage state or structure component after the fire. The damage state, it means the post-fire condition of a component, which is mainly determined by the different level of repair actions. While the engineer demand parameter, which is a response quantity for estimating damage, this parameter will use to estimate the damage. Where we get those engineer demand parameter, it's the response quantity of the building. Definitely, it comes from the second step, probabilistic Fire-thermo-mechanical analysis. So in this step, it will output the probabilistic distribution of those response quantities. And these two, damage state and engineer demand parameter, these two is connected by the fragility function. So the fragility function is the probability distribution reaching or exceeding our damage state. So ultimately, the convolution of the fragility function with the probability distribution of the engineer demand parameter, and will tell you the probability of a structure component reaching or exceeding one damage state. But it's a condition to follow the QF, and the fire happens in the location FILI. So this calculation process will repeat it for different fire load. Ultimately, we get the fragility function as a function of fire load. So the damage state of a structure component now it's at one specific damage state. The damage probability distribution of a structure component at one specific damage state. It will be the difference between two successive damage states. So here is just reaching or exceeding, and now this part calculation is ultimately this part will tell you the probability of a structure component at one specific damage state. So this is how we calculate the probability of a structure component at one specific damage state. So from this, we may already know that we need to define the damage state, right? We also need to know the fragility function, and we also need to propose the engineer demand parameter. And all those function or parameter, they need to be hazard specific. For fire hazard, it has to be fire specific. But all those is try to address the damage state. So before we develop those parameter, develop those classification damage states, first we need to know what's the characteristic of fire damage. That's the next slide. So the characteristic of fire hazard, as we mentioned, it's multiple physics. So it will have some damage, section damage due to the heat penetration, sporing, cracking, and also it will have some damage which is related to the thermal expansion, the residual deformation. So both types of fire damage need to be addressed by this framework. So corresponding to the two types of damage, and we have defined the two sets of engineer demand parameter. So one engineer demand parameter try to address the section damage due to the heat penetration, while the other set of engineer demand parameter try to address the residual deformations. So for the section damage, and usually the heat penetration in practice, when the concrete strength, the temperature of the concrete exceed 300 Celsius degree, and the concrete will turn to the color of the concrete will turn to pink. And in practice, those concrete will be replaced. So the engineering demand parameter we defined to address the section damage due to heat penetration is D300. Here's the definition. So D300 is the heat penetration depth of the isotherm with peak history temperature equal to 300 Celsius degree. So while for the residual deformation, and we have proposed different engineer demand parameters for different structure components. For the column, what we have defined is a residual inclination, and which is a definition is a lateral displacement at the top of column over the height of this column. While for the flow system, what we have defined is the residual deflection ratios, which is a deflection of a flow system over the span of this flow system. So this engineering parameter, it tries to adjust the section damage due to heat penetration, while this set of engineering demand parameter try to address the residual deformation or structure component after the fire hazard. So now I would like to show you how we define the propose the classification of damage states. Let's take in the heat penetration damage, for example. So basically, in the development of the classification of damage states, we need to make sure each damage state corresponding to each level of repair efforts. While for the heat penetration damage, in practice, basically the level of repair efforts is mainly determined by the heat penetration depth of the isosome, which is equal to the peak temperature equal to 300 Celsius degree. That means that this parameter is the engineering parameter we have defined to adjust the section damage, which means that engineering parameter, this 300 determines the repair efforts, while the repair efforts determine the damage states. That's why when we define the each damage states, we can using a range of the engineering parameters. So basically, for each damage state, we propose a range of the engineering demand parameter with an upper bound and a lower bound. So this is how we classify the damage states. It's mainly based on the engineering demand parameter. So for each damage state, there will be a range of the engineering demand parameter with a lower bound and the upper bound. Next step is the fragility function. The fragility function for earthquake engineering, they mainly develop the fragility function based on test data. But the structural response under fire, the test data is relatively limited. So we're using a different way to develop the fragility function. As we have mentioned, and our classification of damage states is mainly based on the engineering demand parameter directly, a range of the engineering demand parameter define a one damage state. So once we get the probability distribution of the engineering demand parameters, we can calculate the probability of structure component at one specific damage state directly. But in reality, as I mentioned, uncertainties exist everywhere. So those lower bound or upper bound, it also has some uncertainties. For example, the different engineer may have different opinions about those threshold values. So we assume those threshold values follow a log normal distribution. So ultimately, the log normal distribution of the lower threshold value becomes a fragility function for one damage state. So once we get the probability distribution of the engineering demand parameter and the convolution of the fragility function and the probability distribution of the engineering demand parameter, ultimately can tell you the probability of a structure component reaching or exceeding one damage state. So this is how we have we define the fire-specific engineering demand parameters. We define the fire-specific classification of damage states, and also we propose fire-specific fragility functions, and also about how we develop those fragility functions for fire-specific damages. And so based on those definition of parameter functions, we can conduct the damage analysis and get the probability of a building collapse. And if the building does not collapse, we can calculate the probability of a structure component at one specific damage state. And those probability and will allow us to do the loss analysis. So in the loss analysis, first we needed to identify the total replaced cost of a building. If the building collapse, and the cost will be the total replace. It including the cost for the total replace cost for the structure component and the non-structure component, and also for the content in the building. And the total replace cost for a building for the structure component and non-structure component. And those costs can be estimated by some construction manual data. For example, in the United States, the IS mean data set has been used very frequently by people in the industry field. And while for the content replace cost, the FEMA's recommendation is that the replace cost for the content in a building is equal to the replace cost of the building, total replace cost of the building. It means the replace cost for the content is equal to the total replace cost of the structure and the non-structure component of a building. If the building does not collapse, so we need to identify the repair cost for each damage state for each structure component. So since the repair cost, it really determines the repair action has been used. So here's, we have already identified the different repair actions from the literature and talking with people in the industrial field. And we identify the repair actions for each damage state and for each structure component. And based on this one, we can calculate the mean repair cost for each structure component at each damage state. So this is the mean value for the repair cost. And also some literature have recommended those repair costs also follow a log normal distribution and has a relative high coefficient of variation ranging from 0.6 to 1.1. And these are the loss functions. These are the loss functions. So now we know the replace cost of a building and the replace cost for the content, and we have the loss function for the each structure component at each damage state. And now we can do a lot of analysis. And here I would like to show you how, as an example, I would like to show you how we have calculated the expected loss for a building. So basically, in this calculation, we need to consider the probability of building collapse. And also we need to consider the probability of component at different damage states. So if the fire is just at the fire location FIL and the fire load is QF, and the expected loss of the building in such a scenario is a weighted summation of the expected loss for the collapse scenario and the non-collapse scenario. While for the non-collapse scenario, we need to consider the repair cost in fire region and non-fire regions. And this will be needed to repeat it for different level of fire load. And ultimately, we get the expected loss as a function of the fire load. So this function, the expected loss as a function of fire load, will convoluted with the probability distribution of the fire load, and ultimately can tell us the expected loss of the building when the fire happens in the location FILI. And this needed to be repeated again for different fire locations. So the total expected loss of the building will be the weighted summation of the loss for different fire locations. Here the weight is the probability that a fire happens in this location, one specific location. This is how we calculate the expected losses. Definitely the information output provided by the previous steps can help you to do more analysis and more interesting results can show, and those results can help, can support the decision making. And now this is, I have already introduced the overall structure of the framework we have proposed and what we have done to make those framework really works for the fire hazards. And here I would like to show you several case studies. And this is a case study and the thin 5-story reinforced concrete building. And it's a 5-story reinforced concrete building. I think it means reinforced concrete. And it's an office building and designed according to the Canada code. And according to the IBC International Building Code, it's type 2A and the fire resistance is 1 hour. And these are the damage we considered in this framework. And we consider the structure damage, fire damage to structure component. We consider the fire damage to non-structure component, and we also consider the fire damage content. In the structure component, we consider mainly focus on column and the floor systems. And the floor system including two parts, beam and slab. While for the non-structure component, we mainly focus on the interior wall and the exterior walls. And here's some cost data, which is provided by either we refer to FEMA recommendation or we estimate according to the construction data manual data set. So here's a case one. We assume all the fire happens in a 7 meter by 7 meter compartment, but we consider the different location from the first story and to the top story. But we assume all the fire is confined in one location, 7 meter by 7 meter, but consider the different location. Basically, the fire will move in each compartment. And the expected, here's some example fragility curves. And here's some fragility curve for the column when the fire happens in the corner compartment in the first story. So when the fire happens in this location, and this is the fragility curve as a function of fire load we have get. This figure is the residual inclination of the fire of the corner column, while this one is the heat penetration depth of the corner column. And this one is the residual deflection of the floor system above the compartment, this compartment. And basically, those curves is basically it can tell you the probability of a structure component reaching or exceeding one damage state. So as a function of the fire load. And we needed to get this type of information for each structure component in a building and for each fire locations. And ultimately, we are able to calculate the expected loss of this building. And the loss will be 187,900. So if we analyzing the contribution of each component, content, non-structure component, and the structure part, and basically we found that the most fire loss is come from the fire damage to the content and the non-structure components, while the damage loss due to the structure components is only accounted for 14%. And this a relative low ratio. Here's some explanations, the reason why it's low. Since in our framework, we only consider the direct fire loss. So we didn't consider the indirect fire loss. But when a building is damaged by fires, if the structure system is damaged by fire, it usually requires more repair time and repair efforts. So if we consider those repair time, repair efforts, and definitely the indirect loss, indirect due to the damage to the structure system will be increased significantly. So the ratio, if you consider the indirect loss due to the fire damage to structure system, the ratio of this one will be definitely will increase dramatically. This is also one future research direction for this for our project. And also we have considered another case. And in the case 2, we assume all the fire is confined in a 21 meter by 21 meter compartment. Also, we consider the different fire locations. And we found that the fire damage loss increased dramatically. And the last scenario is the case 3. And we assume the fire starts in a 7 meter by 7 meter compartment, but have the probability of 5% to spread to area of 21 meter by 21 meters. And we're using those event tree to analyzing the probability of each fire scenarios and calculated the fire loss. So, and we found that compared to case 1, the case 3's fire loss has increased by 28%. So here's our conclusion. So basically, the first one is both the fire safety and the function recovery require a comprehensive framework for estimating the fire risk to a building. building structure. So this such type of framework, for one thing, it provides a methodology for the risk-informed performance-based design of the building structure by protection. And also the output from this framework will facilitate the analysis of buildings recovery after the fires. And in our research, we have adapted the PBEE methodology for fires, but we define the we consider some specific characteristics in our framework. And first, we consider the interaction between each structural component within a building. And then we also have developed the probabilistic material models for high temperature, for concrete, and also for the steel. And also we have defined a fire-specific durable set of engineering demand parameters to capture the multiple physical nature of the fire damage. The last one is we define the fire-specific fragility function and loss function based on the literature data for post-fire repairs. And also I have shown you the 3 case studies. The case study have shown that the direct fire loss due to structural damage is limited. But one point needed to keep in mind is that this framework only considers the direct fire loss. If we consider the indirect loss due to the fire damage structure component, the fire loss due to the fire damage structure system will increase dramatically. And also we have shown that the case study have shown most of course data, if we just consider the direct fire loss, it's mainly come from the content and the non-structural component in fire region. And also the results have shown fire spread will increase the fire damage loss significantly. And here's some future research. For one thing, we want to improve the damage and loss analysis of the non-structural component and content. Since in the current framework, this part is simplified, is significant. So we try to refine those methodology to make the damage analysis and loss analysis of structural component and non-structural component content more correct. And also we would like to include in the calculation of indirect cost. And the next part is how to accelerate the prediction structural response under fire. The current one is still the physical-based model. So our next step is try to develop some data-driven model to analyze a whole structure system. There's some existing research here which have developed for different type of data-driven model, but they are mainly focused on the structural component level, a beam or column. So we try to develop some model which is data-driven model to analyze a whole structure system. The last step is to adapt this framework for the other type of building. Current framework are mainly for reinforced concrete structure. Definitely it can be changed for use for timber structure, steel structure. And what we need to do is to define those material specific engineering parameter and fragility function and classification of damage states. And recently we get funding from the National Fire Protection Association and to move this research here further. Yeah, that's all. Thank you. Any question? Welcome.
Dr. Ni, thank you so much for your presentation.
Thank you.
My name is Anwar. I'm actually one of the postdocs here at PolyU. I also work in a very adjacent area to yours. I do structural simulation and fire. And just let me start by saying this work is wonderful. It has touched upon many very important aspects. I don't think many people actually consider the variability in concrete material properties, for example, in fire. Another thing you touched upon is actually you integrated all 4 important criteria in your framework, which I think also is missing. There are some questions in the chat already. We have a question from Professor Asif Uthmani, and his question, he says, this is great research, but do you think it has a chance to ever be used, considering that the peer method has not been used widely by earthquake engineers?
I think the one thing it's so far the kind of framework is very difficult to be used since, as I mentioned, the prediction or the structural response is still physical based. And it's physical based, it means it's still finite elemental method based. So the analysis, if when you try to consider the incorporate the uncertainties from different variables, so you have to using some Monte Carlo analysis. So it will be very time consuming, even you just analyzing one building. So I don't think the kind of framework can be used. So what we can do to make this framework practical, I think one thing is we need to develop some data-driven surrogate model to replace the current prediction, which is physical-based ones. And the other thing is that we need the current one in the damage analysis. We only consider the damage to the beam and the column from system. But one component we ignored is the connections. Sometimes the fire damage the connections and which will leading to the collapse of the building. So we needed to make the damage analysis more extensive, cover more structure component. But even we consider all those components, and since the analysis, even for one building, it takes a long time, several weeks to finish the analysis. I think they still have a lot of efforts to simplify some part to incorporate something more important, to make this framework practical. I know the PBEE framework does not use very frequently in earthquake engineering. I think the one thing is that if we use for the design, if some company can do this type of analysis, but it's really difficult to make this framework, to be known for everybody, every engineers in the industrial field. I think one thing we can do is also to have more educations in structural engineering to propose to advance the application of such type of frameworks.
I understand. We also have another question from Professor Uthmani, and he said, you have focused on the last 3 stages of the peer methodology and simply considered the spatial analysis, the spatial uncertainty for the IM. Where do you think that the greatest uncertainty lies in the whole process? Is your analysis effort consistent with the nature of the uncertainty you're facing? I think you touched upon this when you said, for example, you didn't consider connections and you need more details. Would you like to elaborate a little bit more for this question?
Yeah, for the uncertainties, and since we mainly focus on the last steps, but I have talking with some other research in this fire research community.
Dr. Ni?
Yeah.
We've lost you. Please wait 1 second, please. Can you hear her? Dr. Ni?
Yeah.
Yes, you're back. Please, I'm sorry. We couldn't hear you. Please, again, I'm sorry.
Yeah. So our framework currently, we simplified the estimation, the probability of the fire occurrence in one location, and the step 1 fire hazard analysis. We simplify this step, but in my opinion, the most uncertainty is come from these steps. And but the reason we focus on the last 3 steps is mainly because my research is focused on structural engineering, and we do welcome any collaboration in the field of fire dynamics or fire science, which try to refine our analysis in the first step.
Right. So you think the fire it contains the most uncertainty? Is that correct?
I think so.
But also in earthquake engineering, earthquakes would represent the biggest uncertainty. But what they would do is they would have more of just apply as many possible earthquake scenarios as possible and see the response from that. Do you think we can do something similar for fire, where we try to create a library of fire scenarios that may occur so we can cover as much as possible?
Yeah, well, I think we can do, but we can incorporate the most current research about traveling fire and compartment fires, and to make the fire analysis more extensive and comprehensive. Yeah, definitely we can do that.
All right, thank you very much. We have a question from Associate Professor Ahmed Yunus from the Fire and Explosion Protection Lab from the NIS in Egypt, and he's asking about slide 26, expected fire loss. He would like to know that you didn't share in your calculation of the rate and direction of the wind during the ignition. Dr. Yunus, if you'd like, you can unmute yourself if you would like to talk.
Yeah.
So slide 26, if you can. Dr. Ahmed Yunus, would you like to go on the mic? I think he cannot, or he cannot hear.
It's fun. I can answer the question.
Please,
so basically, yeah, he said we need to, I didn't share the calculation of the rate and the direction of wind during the ignition. So basically in our framework, current one in the fire hazard analysis, this that step, we just refer to the recommendation methods in the yellow code. Basically, it calculates the probability or fire happens in one area. So it's a very simplified method. So if we want to consider the rate and direction wind, it mainly we would like to consider more uncertainties in the fire hazard analysis, and which is
I completely agree with you. But I also, if I'm not wrong, you're considering a building, so not necessarily an open structure. So would wind play a significant role if you're looking at an internal fire?
I think it's maybe have some impact for the tall building fires. If they have, but since we mainly focus on the internal fire in a building, so it's not a significant factor if we just consider some low-rising building or two-story or three-story buildings. But definitely, if we want to extend this framework for tall buildings, and we consider the tall building fires and maybe the wind will be impacting factors.
Fantastic. Thank you very much. We have another question. I think we have this time for this last question. Zheng Yangfu wonders about the time, the computational time for that 5-story structure that you shared. And he also wonders if you can incorporate AI and machine learning to accelerate that time.
Yeah, that's our future research direction. So basically, if we analyzing a 5-story building and on a normal desktop rather than supercomputers, and it will take more than 19 hours, and for one file scenarios. But if we simplify the building, for example, I remove the slab and some upper stories, and the calculation time will be reduced to almost 8 hours. But it's still not enough for such a type of framework. So our next step is try to propose some data-driven surrogate models based on the machine learning techniques.
Right. So speaking of that, if you may, what software are you using to do your analysis?
Sophia, which is a software developed by my postdoctoral supervisor.
Right. Yeah. So
and Dr. Francis. Yeah.
Can you do parallel processing using Sapphire?
Yeah, it's current one. The most current version it works. Maybe the older one I don't think works, but they have this software is developing every year. So in the past few years, it incorporates different mature models, probabilistic mature models, and different computation techniques, and it can be used parallels. Yeah.
Right. So you think can it be deployed on high performance computing machines or on supercomputers, as you had said earlier?
Yeah, it can be used, but for the paper I have published,
Dr. Ni, I'm sorry, we lost you again.
Oh, can you hear me now?
Oh, I think it's your connection not very good.
Oh, I'm sorry.
Yes, please continue.
So when I do this analysis for the paper we published in the structure safety, we didn't use the supercomputer centers, but definitely the current Sophia can use as a parallel computation can be used in Sophia. It will accelerate the calculation dramatically.
Fantastic. I still think we have time for the last question, again asked by Dr. Ahmed Yunus, and he says, how can you determine the degree of damage practicable to be classified as dangerous or not? And that brings me to my question: how do you determine if there would be structural collapse from your finite element model or not?
Yeah, basically, if it's a building in the analysis, when the structure, it really for the reinforced concrete structure, and I check each scenario. Since usually the reinforced concrete structure is very far resistance, and there's no collapse happens, we can visualize the damage of the building for each model. But for the steel structure, the collapse really will happen. But since our research is mainly focused on the reinforced concrete structure, and we do not to identify the failure criteria for the other type of structures. For the current research, I don't think there's any collapse happens in the building since we visualize each scenarios.
I understand. Thank you. Thank you very much, Dr. Ni. I think that's our time. I will hand over back to Dr. Xinyan Huang for the closing. Thank you so much for your time, for answering all the questions.
Thank you for your question. It's very inspiring.
Okay, so I guess we will editing the video and post it online next week. And that will be all for today's presentation. Thank you, Dr. Ni, again, for a very nice talk.
Yeah.
Okay, bye-bye.
Bye-bye.